So, I've showed you some video evidence and some actual evidence that moving charges get bent, get deflected, feel a force from magnetic fields. The question we want to ask today is how big? How do we calculate the magnitude of the force? Here is your first equation for this unit. Magnetic force on a moving charge. So my abbreviation for magnetic force, it's a force, so as always, capital F, but it's not Fg, gravity, it's not Fe, electric force, it's not Fc, centripetal, Fb for magnetic force. It's equal to Q V B. The V is a lowercase v, it's not voltage, it's speed or velocity. So Q equals the charge in coulombs. A bigger charge will feel a bigger force. A smaller charge will feel a smaller force. V equals the velocity in meters per second. If you go faster, you're cutting through more magnetic field lines per second, and so you'll feel a bigger force of deflection because you're going through more of the field in 1 second than if you're going slower. And it makes sense that there is a B there. That is the B field. That's my abbreviation for magnetic. And that's in Teslas. Yeah, a stronger magnet would apply a bigger force. Except we have to add one more restriction here. Can you put beneath the V and the B a little perpendicular symbol? They have to be at right angles to each other. If they're running parallel to each other, no deflection will occur. I'll get into that more, Sarah, in more detail. Sometimes the charges don't move perpendicular to the magnetic field. If that's the case, we have to do a component. I'm not going to be asking you component questions in this unit, though. But sometimes you'll see it given as F equals QVB sine theta. This is really the correct formula. Because if they're at right angles to each other, if they're perpendicular to each other, how big is angle theta in degrees? What's the sine of 90? 1. And that's where you get QVB. If they're parallel to each other, how big is angle theta in degrees? 0. What's the sine of 0? You get no force. Okay. So if charges move parallel, then sine theta is 0. You get no force. If they're perpendicular, you get sine theta is 1, and you get QVB. So the key idea, or one of the key ideas here, is that the maximum force is experienced when particles move in a direction that's perpendicular to the magnetic field. So far, so good, Lena? Let's use this. And believe it or not, we're only about 2 little leaps of logic away from designing the Large Hadron Collider. Okay? A proton moving at 1.7 times 10 to the 6th meters per second enters a 0.15 Tesla. 0.15 Tesla field, big, small? What was a big field?
Big field's like 4.
4 or 5. This is pretty big, okay? This is being caused by a large electromagnet. This is not a simple rare earth magnet. At right angles to the field, what's the net force on the proton? Let's call that part A. And what's the net acceleration? Let's call that part B. What force do they want me to find? The what force? That was, you might recall, we're doing a little review, code saying you don't need to worry about a free body diagram. All you're going to do is you're just going to use the plug and chug equation. It's a magnetic force, so magnetic force is going to be QVB. I did a quick double check. It does say we're at right angles, so we are perpendicular. We are okay. I think on your formula sheet, I think I put the perpendicular symbols in the equation. Yeah, I think, okay. Q, are you ready? It's a proton. Oh, this is good review, Mr. Duke.
1.67 times 10.
That's the mass. Nice try.
Oh my god. 1.6 times 10 to the positive 19.
I think, to the negative 19, because the positive 19,
would it be
that would be a massive, because remember, 1 coulomb
Yes.
is massive. That would be many, many, many
It's been a
billion,
unit.
trillion,
You tried.
quadril,
It's been a unit now.
heptillions,
No.
hextillions. It's big.
Vote of head to unit.
V speed, 1.7 times 10 to the 6th, 0.15. How big is the magnetic force? Now, force is a vector, but I'm just finding the magnitude because I didn't give you any kind of direction here. If I gave you a picture, we could say up the page or down the page, or remember we learned new symbols into the page. That was an X, like the tail feathers of an arrow going away from us or out of the page. What do you get?
4.08 times 10 to the negative 14.
Sorry?
4.08 times 10 to the negative 14.
Is that right, folks?
Yeah.
Force is measured in newtons. Is that big? Well, it may seem small, but what does part B want us to find, Eric? How do I find the acceleration if I know the force? Yeah, F equals ma. So the acceleration is going to be F divided by m. It's going to be 4.08 times 10 to the negative 14. Caleb, now you're on mass of a proton.
1.67 times 10 to the negative 27.
Good. I think you're going to find this is a massive acceleration, and therefore on this scale, it's a massive force. Of course, you're going to use your answer button, right? Munir, what'd you get?
2.44 times 10 to the 13.
She's hauling faster than the speed of light.
It's not a speed.
It's an acceleration.
And so it won't be traveling long enough with this acceleration to crack the speed of light. Whatever situation I was pulling this from, trust me, nature would intervene, and either we'd be out of the magnetic field before we hit the speed of light, or something else would be going on. Or if you started getting close to the speed of light, what happens to the mass? Remember from last year? No. It increases. So if this gets bigger, your acceleration gets smaller and smaller. In fact, the protons in the Large Hadron Collider, when they're going near the speed of light, they are massively massive. They are not 1.67 times 10 to the negative 27. They are significantly larger than that. Let's build a particle accelerometer. Particle accelerator. Let's build the Large Hadron Collider.
That's how Barry Allen got super.
Okay. What shape is the Large Hadron Collider when you've looked at it from above? Why is it a circle? Why are almost all particle accelerators a circle? Consider an electron as follows. Which way is this electron moving? To the? Now, our right-hand rule does not work for electrons. An electron moving to the right is the same as a proton moving which way? So let's all use my whiteboard, my screen behind me, or you can hold up your piece of paper vertically. Point your right thumbs to the left. Which way is this magnetic field that it's entering pointing? What do those X's mean? Into the page. So hold your hand out, extend your fingers like you're high-fiving straight into the page. Which way is this electron going to feel a force right when it hits the magnetic field? Okay, pause. So right here, the electron is going to feel a force down, and it's going to be bent that way. You okay with that? Now I have an electron moving down and right. We don't do electrons. That's the same as a proton moving up and left. Point your right thumbs up and left. Magnetic field and just still into the page. And can you see now the electron's going to get pushed down and left. Now the electron is moving straight down the page. Our right-hand rule doesn't work for electrons. We point our thumb up the page, extend fingers into the page. Now which way will the electron feel a force? In fact, what you're going to see is that the electron gets pushed into a, looking for word begins letter C. And this is why most particle accelerators are circular. It's really easy with some cleverness to bend moving charges into a circle. In fact, we can either predict the radius, calculate the radius if we know the charge, or if we know the radius, we can determine the mass or the charge based on how they're behaving. And this is how we start to separate out all these subatomic particles. In fact, we can say this. Magnetic force is what's pulling me in a circle. That one is not on your formula sheet. Oh, what was our new equation for magnetic force? Q, V, B. And then circular force is always, don't write this down, just look up. MAC, except which version of A do you think I'm going to use here? It is obvious if you think about it. The one with the V in it, of course, because there's a V on the left-hand side, yes? So why wouldn't I use the V squared over R? Yes, a V will cancel short, but we'll tackle all that. My point is, we can say if a charge is moving in a circle, magnetic force is what's pushing us in a circle. And so I like example 3, I like example 3, I like example 3. Example 3 is a nice question. An electron moving that fast enters a perpendicular Tesla magnetic field and traces out a circular path. What's the radius of this path? This question is asking me, Lena, to find the radius, but what path are we tracing out? Looking for the letter C. So we can say magnetic force is pushing me in a circle. Is that okay, Mitra? Magnetic force is on a charge QVB. And I'm going to go with mv squared over r. Does a v cancel here? They're both on the top. If I divide the one v over to the other side, I can say that that and that will cancel. The most common, and I don't use this word very often, dumb mistake, sloppy mistake, preventable mistake. Where is the R right now? On the one that drives me crazy is kids will get to this line and they'll go, oh, I'll divide the MV over, now I have the R by itself. You don't. You have on the R on the bottom by itself, which does no good. Instead, what I'm going to do, Sarah, is times the R to that side. And what will I do with the QB? Yeah. R is going to be MV over QB. Is that okay, Lena? And Lena, you can see if we're actually doing subatomic particle physics, if we know the radius, we can also use this to either figure out the mass of these subatomic particles, the charge, or the velocity. If we know some of the other ones, we have other ways to measure the other ones as well. By the way, from Physics 11, what is mass times velocity? Momentum. You can also use this to calculate the momentum of objects, and now you can start to collide them together. Wham! They collide. Remember that from last year? You can start to do some particle physics. Let's plug in the numbers now. The radius is going to be m. It's an electron. I always remember it's 9.11, but I never remember the 10 to the negative 31. The speed is 3.2 times 10 to the 7th. Q, it's an electron. I don't put the negative in here because we're doing a scalar equation right now. We don't need a negative radius. And the magnetic field is 5.45 times 10 to the negative 4. I hope I've made up good numbers, but who knows? I'd love to have a radius of about 0.5 meter, but I have a feeling I'm way too small. Really? Oh, that's not bad. Okay. 33 centimeters, that's about, okay, that's not bad. That's measurable. 0.334, I'll even go one extra sig fig just for giggles. What if I sent a proton through this same system? Would the radius be bigger, smaller, or the same size? Well, if they went at the same speed, v would be the same, q is the same. Oh, what? So a bigger mass would give me a proton wouldn't be deflected as fast because it's more massive, and so it would have a larger curve, a bigger radius, which in hindsight makes good sense. Example 4. This is from the January 1990 provincial exam, in case you're wondering. It says, as shown above in the above diagram, a proton, by the way, let's make sure their physics is correct. Right when it enters the magnetic field, what direction is the proton traveling? Up the page. Everybody, let's point our thumb up the page. What direction is the magnetic field? What do those X's mean? So my high five is going to go into the page, and you can see my palm is pointing in the direction of the deflection. It will trace out that path. I'm using this screen, but if you're using that diagram, you need to lift your page up and hold it vertical. I mean, you have to hold it vertical. Now that'll work, okay? But you can't look at my vertical screen and look at that flat piece of paper. If I was doing it, looking at my piece of paper on my desk, I would be pointing my right hand straight into my desk like that, and I still get that lovely curve. Okay, so I agree with the physics. Kevin, what does this want me to find?
The speed that enters magnetic field.
What path is this proton tracing out? So magnetic force is what's pushing me in a circle. QVB equals mv squared over r. Yay, one of the v's cancels. Now they want the speed. How will I get the v by itself? Times by r divided by m. Square root? Nope, no need to square root. So v is going to be q b r all over m. Is that correct? I think. So the speed is going to be, it's a proton, 1.6 times 10 to the negative 19. B, 0.02, it's 2 times 10 to the negative 2, but that's less typing. R, 3.25 meters. And the mass, Caleb, what was the mass of a proton?
1.67 times 10 to the negative 27.
Which I'll have forgotten by September, but it usually sticks with me for the rest of the year once I do electrostatics. How fast is it going? And hopefully it's less than the speed of light. Should be.
It's going on 6,200,000.
You read it to me in scientific notation, please. What point? What?
0.23 times 10 to the 6.
Fast. What if we wanted to speed it up? Bigger magnetic field? Because we can't change Q. Yeah.
So would the proton be experiencing like a different time as well?
Yes. Oh, yes. And we have to take that into account. So, for example, UBC manufactures radioactive isotopes for, I think, for Vancouver General, for VGH, for cancer treatment and things like that. And I believe they have some type of tunnel or pipe that actually ships them underground to there. But they move at a speed that they have to take into account that the radioactive decay that that those particles are undergoing is not based on our time, and they have to make sure that the hospital is aware of that. Otherwise, they won't be at a level of radioactivity that the hospital is expecting. Yeah. Oh yeah. Relativity shows up in really cool places. What if we have a bunch of charges stuck in a wire holding hands? Well, if one moving charge will feel a force, a bunch of charges stuck in a wire holding hands should also feel a big force. So if we have a wire carrying current perpendicular to a magnetic field, it will also experience a force. And the direction, again, is going to be our right-hand motor rule, but instead of pointing our thumb in the direction of the single particle, we'll point our right thumb in the direction of the current, because that is all the particles. Depends on three things: the strength of the magnetic field, the magnitude of the current, and the length of the wire inside the field. And we can derive it by starting with our equation for a single charge. Now, I want to somehow bring current into this. I know that current is defined as coulombs per second. So can you rewrite that equation, Kyle, and get the Q by itself? Times what over? Let's use nouns and not pronouns. The times T over. So I can say F equals IT VB. Underline those two. Instead of T times V, V times T, you know what that is? That's distance if there's no acceleration, because D equals VT plus a half AT squared if there's no acceleration. So I can replace this here with distance. Where this distance is the wire length, the length of wire in the magnetic field. What's I? Current. What's B? Okay, because it's a wire length, what letter do we use for length? As an equation, we say this. So here is another equation for magnetic force, and you can put in brackets on a wire, and it is Bill. I always make my lowercase l as a cursive L so you can tell it's not a 1. I think I even did that on your formula sheet. I think I looked for a font that made the L a cursive L because I didn't want it to look like BI1. Or I did, yes? That was something I'm fussy on. Oh, same restriction as before, though. The magnetic field, the current, and the length of wire all have to be at right angles to each other so your right-hand rule works. So, example 4. Here is a wire. You're going to have to kind of decipher my stick figure diagrams, but it looks like the current in the wire is moving to the right. Yes? What direction is the magnetic field? Down the page? Okay. It says find the magnetic force and the direction. Let's see if we can find the direction. So you can decide if you want to follow me up here. If you're going to follow me up here, you want to hold your paper vertical, or you can try this on your own on your desk. But the right-hand rule says we point our right thumb in the direction of the current. We extend our fingers like we're high-fiving in the direction of the magnetic field. Which way is the magnetic field? Down. So I'm either, Kevin, going to need to yoga bend like that, or get kind of like that. But no matter what I do, and by the way, now, ready? Do it on your own piece of paper. So on your own piece of paper, point your thumbs to the right. Which way is the magnetic field? Straight down your page, so your hand should be pointing towards you. And if it gets awkward, rotate the paper 90 degrees. And now, or spin it 180. And you'll just have to translate that down the page became up the page temporarily or whatever, okay? So if you're really finding you're bending weird, spin your paper. What direction? I'm getting, boom, boom. I'm getting the direction is going to be into the page, or if I was really lazy, I could write it like that. Let's find the magnitude. They're wanting us to find force. Is it on a single charge? Is it on a single charge? Say no. It's on a wire with current. So, because I have two equations for magnetic force, that's really the only medium tricky part. I have to decide which one I'm going to use. And again, notice the magnetic field, the current, and the length are all at right angles to each other. Magnetic field is 6, current is 5, and the length is 0.7. Hey, I can do that in my head. 6 times 5 is 30. I think it's going to be 21 newtons. And you'll notice the force just got way bigger. I think one of the ones we calculated for the proton a while ago was like 10 to the negative 12 or something ridiculous like that. Here, 21 newtons, that's force. That's the equivalent of holding a 2 kilogram mass in your hand, roughly. I'd feel that. Suppose a 5 centimeter piece of wire carrying 12 amps experiences a force of 1.5 times 10 to the negative 3 newtons. What's the magnetic field strength that it's inside? Okay. This question wants me to find magnetic field strength. We have the magnetic force on a current carrying wire. Matt, how would I get the... Oh, which of those is magnetic field strength? What letter? How do I get the B by itself? Now, I like this question. I like this question. I like this question. This is also one that drives me crazy because I've lost track of how many times I've said to a student, find me the magnetic field strength, and they find me the magnetic force. They find me F, which, first of all, I gave them in the question. But they go through all the numbers, and at the end, they proudly write F equals 1.0 times 10 to the negative 3, and don't do that. Field is B. So it's going to be 1 times 10 to the negative 3, or 0.001, 12 amps, and 0.05. And I get 1.67 times 10 to the negative 3 Teslas. Not huge, but not small. About 1,000 times stronger than the Earth's magnetic field. Ish. Cool applications. There was a movie that came out. It's well over 20 years old now. The book also sold well. It's called The Hunt for Red October by Tom Clancy. And if you watch the movie or if you read the book, the premise is that Russia has developed a nuclear sub that's undetectable because it moves through the water with no moving parts. They call it a magneto-hydrodynamic or caterpillar drive. This is how it would work. You can design an engine underwater with no moving parts. What you have to imagine is something I couldn't draw on here, so look up for a second, all of you, Caleb, you too. Imagine that there is a conductive plate right here on the outside facing us. Okay, I need to remove that so we can see through it. And so what we have done then is this conductive plate, we've charged it so that charge is flowing through the seawater back to the hull. That's what those X's there mean. What direction is the current going? Into the page. That's what those X's there mean. What's the current traveling through? What are the charged particles? Seawater. Not using wires to connect it, just using seawater to conduct the electricity. Seawater pretty conductive? Oh, yes. Okay. What direction is the magnetic field Magnetic field lines always point from what to what? North to south. So all of you right now, if you want to add some arrows like that, and you can label that as B, that's your B field. So which way is the current moving into the page? All of you right now, looking at your desk version, point your thumbs into the page. What direction is the magnetic field? Down the page. Point your thumbs into the page, and now high five. Rotate your hands so the fingers are pointing down the page. Psst, like this. Yes? What direction is the seawater going to feel a force? Out the back, like a jet engine with no moving parts. And this will cause this submarine to go forward. Right? That's the direction of your force on the water. Water will get sucked in on the front and get pushed out at the back. But since there's no moving parts, it would sound to someone who was trying to detect this submarine like waves. Are there already waves on the ocean? I don't think you could pick it up. You'd be hoping to pick up maybe the generator noise inside the submarine that was creating the electricity in the first place, but you certainly wouldn't pick it up from the outside. That was the plot line. The physics in that novel was okay. There's all sorts of other cool ways as well. We'll talk about how you could design a space station launching system through this. Our third equation today is the magnetic field of a solenoid. Up until now, I've just been telling you how big the magnetic fields were, but we can control the magnetic fields with a great deal of accuracy. So when we're talking about a solenoid, we can vary several things. We can vary how many turns of wire there are. We can vary the length of the solenoid, really big, really small. We can vary the current running through the wires. All of those will affect the strength of the solenoid. So Ampere determined that the magnetic field inside a solenoid depended on certain variables. It depended on the current running through the wire. He found more current meant a bigger field, so I is going to be on the top. He found it depended on the number of turns of the wire, because each time you add a turn of wire, you're adding a bit more magnetic field. So more turns meant more field. So N, the number of turns, is going to be on the top. But he also found that it was reciprocally dependent on the length. The shorter the solenoid, Mitra, the shorter the solenoid, the stronger the magnetic field, which makes sense because you've crammed the current in a smaller area. You have more charges in a smaller area overlapping. In other words, he found that the magnetic field was proportional to the number of turns of wire times the current divided by the length, similar to gravitational field being proportional to m over r squared. We needed to put a big G constant there to make the units work. The same way that electric field was equal to q over r squared, we needed to put a lowercase k there to make the units work. We're going to need to put a constant here to make the units work. So in the latter two equations, we need to add a constant, G and K respectively. We need to do the same thing for magnetic field. The magnetic field inside a solenoid is equal to mu naught, mu zero. I had a British physics teacher, and so I call it mu naught, times N times I over L. Who remembers what was big G? More specific, 6.7 times 10 to the negative 11. What was K? This was a nicer one. They're on your sheet. 9 times 10 to the 9th. Find mu naught. It's on your sheet. Pi? What? Did you say pi? What the heck would... Why on earth would...
This is a circle.
Where's a circle? Okay. And then the units are whatever the units need to be to give you an answer in Teslas. This constant has one of the best names ever. It's called the permeability of free space. I love that name. What's the permeability of free space? What's 4 pi times 10 to the negative 7? All of you, for the next few questions, need to try these on your calculator because some of your calculators won't let you type 4 pi times 10 to the negative 7. You'll get an error. If they do, let me know. Oh, there's a second version of this equation. Sometimes instead of telling you the total number of turns and the total length of wire, they give it to you as a ratio for turns per meter. And so the second version of this equation is mu naught lowercase n times I. Hopefully I got those right. I'm going from memory. Yes. In the box up here, you can make a little note. N equals the number of turns of wire. How many times the wire has been looped around the solenoid. What does I stand for? I equals current in amps. And L is the length of the solenoid. In this second box, lowercase n is the number of turns per meter. So if they give you so and so many turns per meter, you'll use this one. What they've already done, Kevin, is they've taken n and they've divided it by L and given you that number down there. If you're actually buying solenoids, that's typically how they're labeled, in turns per meter. So let's use this. A solenoid is carrying a current of 4.2 amps. If a solenoid is 1.2 centimeters long and is made up of 750 turns of wire, what's the magnetic field at its center? Lyndon, what's this question asked me to find? What's the symbol for magnetic field? This is the one where I see kids often find a force because there is a current and there is a length, and they'll go, oh, it's Bill, and they'll maybe say that this is B because they're not sure what to do. Don't do that. What's the symbol for magnetic field? We're talking about a solenoid. It's going to be mu naught N times I over L. Lyndon, what was mu naught?
4 pi times 10 to the negative 7.
N is the number of coils of wire or turns of wire. How many loops of wire? 750. What's the current?
4.2.
What's the length? Don't say 1.2.
0.01.
And this is now, realize what we can do now. We can customize, Braden, magnetic fields. If you need a magnetic field in industry of a certain size, you call up a company that manufactures solenoids. Well, how long do you need it to be? You can tell them how long you have to fit it in, and they'll just put that many coils of wire. How many amps are you running through this? And we can customize magnetic fields to any size that we want. Hugely useful. Hugely useful.
I get an error.
So if you get an error, who's getting the error? What kind of calculator? Casio? On the Casios, and this is a software glitch, instead of typing 4 pi, you'll have to type pi times 4, 10 to the negative 7. It won't let you do scientific notation next to the pi symbol for some reason. Some of yours will. The TIs, I think, will. Okay? And you should get 0.33 Teslas.
It's exact value.
Okay. What if I wanted twice the magnetic field? I have a couple of options, Lena. Double the number of coils in manufacture, double the current, or smoosh it together so it's only half as long. And again, I can't emphasize enough how useful this is. This gives us a customizable magnetic field. Oh, and if you let me hook it up to something where I can vary the current, I have a device that I can change the magnetic field on the fly. You may have seen on TV or in real life at garbage dumps or at old car lots, the big cranes that have a big magnet on the end of the crane to pick up cars, all that is a solenoid. It's a massive solenoid, and all they're doing is they're changing how many amps they send through it with a lever, and they're bumping the magnetic field up enough so they can lift the car off the ground. And then when they want to drop it, they just cut the current down to zero, no more magnetic field, and the car drops. Electromagnets, a magnet that we can turn on and off. Hugely useful. I think no matter 330 if you round it off to 3 sig figs, right? This is meant to be a side. Oh, did they ask for the direct? No, they didn't give me a picture. Here is a side view, so we are looking right through a solenoid like a telescope. What direction is the current flowing? What are those arrows telling me? So, in your mind, in your imagination, let's use my board up here. We're going to hold the solenoid in our hand. Now, the solenoid can either be held this way or this way because we're looking through it like that. We're going to hold it in such a way that our fingers, our right fingers, curl in the direction of the current. Kieran's going to get off her phone before Mr. Good freaks out. Or is that her calculator? Is that your calculator, Kieran? It is? I apologize. So I can't hold it this way. My fingers are curling against the current. I would have to hold it this way. Which way does my thumb point for the solenoid rule? North. This is the north pole of the magnet. So which way is the magnetic field coming? Out of the page. If I wanted to draw the magnetic field, I would go like this. You could add more dots if you want to, but I get the point. How big? The magnetic field from a solenoid. You don't have to put the subscript solenoid. I am in our notes just so that you know that's what we're using. It's going to be mu naught. Did they tell me the number of coils and the length in this question? What did they tell me? Okay, so I'm going to use that other one, which was lowercase n times I, and lowercase n is the number of coils per meter. So it's not much different. It's going to be 4 pi times 10 to the negative 7. Some of you might have to type pi 4. N 2550. 10 amps. And I get 0.032. Teslas, and for a direction out of the page. I've thrown an awful lot at you, I know. One more, we're done. We're going to practice this. And I got a couple of cool videos to show you too.
Instead of writing out of page, would be alright if I just did like this.
I'd probably be okay with that because I tend to abbreviate. Spence, what's number 9 want me to find?
How many turns of wire?
So, and this is my point. This idea of an electromagnet from a solenoid really allows us to customize magnetic fields to whatever we want. So I'm going to start out, I think, since they're talking about a solenoid, I'll write down magnetic field equation for a solenoid. Which of those, Spencer, is the number of turns of wire? How would I get the N by itself?
Multiply the L and then divide the
So it's going to be BL all over mu naught I. Okay. .28 times 10 to the negative 3. 0.3. 4 pi times 10 to the negative 7. 5. The brackets around the bottom. 4 pi times 10 to the negative 7, or pi 4. Double check that I typed this in right. I think I did.
300?
I think that's what I started with when I made up this question. Yeah, 300 coils of wire, 300 turns of wire. And I think the unit for turns of wire would be turns of wire. I threw a lot at you today, Kev, but it's also because I don't see you again for a while, and we're in the home stretch. We're running out of time. So what's your homework? Number 1.
Do we have this one?
Number 2. In number 2, it's saying that this wire is floating in midair due to balanced gravity and magnetic forces. In other words, you can start out by saying Bill, magnetic force, equals little m, little g. And then, Lena, what do they ask me to find in number 2? Which variable? Which of those is magnetic field? B. I think it's divided by IL. I know. I think I'm going to skip 3. Skip 4. We'll do 5. We'll do 6. I think I did. Actually, you know what? Number 6, we did that right in the homework. Let's do 7. We did 6 in the notes. It's the same question. For some reason, I cut and pasted and forgot to change the numbers. Duh. 8 is good. Ten is good. Thirteen is good. 15 is good. Was there a 14? There was a 14. Sure, 14 is good. 16. Sure, 17 is good. Thanks, Sarah. I'll do that one.
Sarah.
Are we doing 16?
No.
16, 15, 16, 14, 15, 16, 13, 14, 15, 16, 17. Although some of those are kind of conceptual ones.